Hey, how's it going all? I just want to do a quick follow-up to my drone test. I'll just label it like part two or something, but just looking at gps.gov. I'll put the link down below. It's just talks a little bit about drones and their precision, and to no surprise, like um, off the shelf, civilian drones have a certain precision that I'm assuming would be similar to what's on our iPhone. If you go to the Compass app on your iPhone, it'll give you GPS coordinates, and and which is, I'm assuming, the way that they have the iPhone recovery feature and all that. I'm not sure if you have to pay extra for that, but apparently there's a feature where you can like locate your iPhone if it's lost or stolen or misplaced or whatever. And so I actually turned that feature on and then just started moving my iPhone around my apartment. And I have a studio, so it's not that big, and it didn't change. And so the error bars, the granularity, according to GPS.gov, for civilian GPS is not as good. I will pull it up right now. And so I'll just tell you what it says here. If you go to gps.gov and then go to GPS, yeah, if you go to gps.gov and then go to the systems tab and then performance and then accuracy, it's still high level, but they actually have some data on here, and talking about GPS enabled smartphones are typically accurate within 5 meters radius under open sky. And so it also then has a little section, why does GPS sometimes show me in the wrong place? And then it says that certain buildings, indoor or ground use, and signals reflecting off things called multipath affect the precision. And so, but they have some data. Again, like for the sake of my drone test, it's over water in like open space. So those type of multipath things would be minimized, if not completely eliminated. But let's just say, let's just use this number for now. It's typically accurate within 5 meters. And so that would essentially be like a 5 meters would be the radius. And so if you have a point, in three-dimensional space, you would have a 5 meter a sphere of a radius of 5 meters all the way around it, representing the uncertainty of that point. Like you could have a drone, again, a civilian drone, or like our GPS phone, our phone with the GPS enabled, like go into that sphere, and in every point in that sphere it would output the same location. And so that's the way we can sort of visualize the error. And so, but I thought it was interesting, if you go down, you can see that it does mention that high-end users boost GPA accuracy with dual frequency receivers and or augmentation systems. These can enable real-time positioning within a few centimeters and long-term measurements at the millimeter level. So I suspect what they mean by long-term measurements is just if you have the ability to, rest a drone in a particular point, and then give like the algorithm time to sort of average out some of the noise, and then move it and then compare it, it can get very, very precise. But it needs sort of learning, some time to like learn about its surroundings. And so that's just my initial take on what it might mean when it says long-term measurements can even get to millimeter level precision. So that to me is incredible, and does not surprise me at all that military grade GPS, like if I were to literally move my phone, let's say my phone was enabled with military grade GPS, and I told you earlier that I moved my phone around my entire apartment and it didn't change its output, I could literally move my phone here, and it would give me a new reading. And so that's incredible, not surprising. Again, with the ingenuity and technology that's on flat Earth right now. But um, that's out there. And so the thing that I wanted to just talk about, which again, if I were to ever, come up with a test with a baller together, I would use GPS just because it's well established, it's out there, it's on our phone. We can't say, oh, we can't touch and feel and interact with it. It's a coordinate system that is readily available for everybody, and most people have phones now. And so, it's a coordinate system. And so I got into debate with ballers about GPS. When you turn that compass app on, you're going to get, latitude, longitude, and an elevation output. So those are the coordinates in spherical coordinate system, if anybody's familiar with that. You have two angles, theta, phi, and then a radius, which is like an elevation if we're talking about Earth being a sphere. And so that's what you get from the compass app. So you get, a spherical coordinate output of where your phone is, our phone is, in three-dimensional space in spherical coordinate system. And so it sets up a coordinate system. It doesn't imply a shape. It's just a coordinate system that, in this case, the elevation and, latitude, longitude, can be mapped to a point, on a ball Earth, but it doesn't change the fact that if I have my phone here and then if I move it for like civilian grade GPS 5 to 10 meters that way, I'm going to get a new reading. And then if I move it 20 meters up, I'm going to get a new reading. And so it gives us a reading of where things are in three-dimensional space. And then the cool thing about the drone test that I propose is you just need a starting point that's understood, how far above the water that it is, and that's easy to measure because you don't have to go that high up above the water as a starting point. And then you would use GPS as a coordinate system to come up with, a path, a predictable path. Doesn't even actually necessarily have to be a straight path either, but as long as you can move the drone in a position that's different than its starting point, obviously, and then just be able to go to those positions in a reliable way, and then suspend something from it and see how that device is interacting with the water beneath it. And so just the fact that this site is telling us that high-end GPSs can go to or high-end GPS accuracy can be within millimeters. So basically military grade drones would solve this ball Earth flat Earth debate in a couple hours, because you could just program it to travel along a straight path. And so the thing that I wanted to mention is that a coordinate system doesn't mean that you're not allowed to move in a particular path. Like, just because you're in spherical coordinate system does not mean that you cannot come up with the coordinates needed to go from one point to another in a straight line. I think I might, if an engineering firm were to do this, you might need two drones. You might need the first drone to shoot like a laser in an arbitrary direction that would be straight, and then only use like the first little piece of it, and then have the second drone, align itself along that line and create like a local straight line, and then use like a daisy chain kind of a solution. It doesn't have to be a laser, but something that can be pointed, straight. And then that could be the thing that sort of calibrates or sets the direction of the straight line early, and then it follows along that path. And so there's ways you can create straight lines within spherical coordinate system or GPS. And so let's say, you can do that even with like civilian level GPS accuracy. You would have these error bars, these big spheres around each point. So there would be uncertainty. But when we're dealing with larger and larger, distances, miles, away from one another, in a flat Earth, we're expecting, this drone to be still relatively, similar height over water. And then the further you go in three-dimensional space, even if it's like, above the water, just above the water, you're going to be, much, much further away from the surface of the water in ball Earth. And so you don't have to have the drone fly from one point to the other and drain its battery. You just, again, have to predefine these points in three-dimensional space using GPS as spherical coordinates, and then have it reliably go to those points. And so, again, with that error accuracy of a sphere of radius, in this case 4.9 meters, if we have civilian GPS. So with that in mind, you could set a path, a route for these drones, and then see how the device interacts with the water beneath it. And to me, it's not really that hard. It's pretty straightforward. Those error bars would then, one nice thing about a test like this is you just do the thing over and over again. So like, for example, let's say this was the point for the second test along the straight line. Let's say in the first test, the drone hits it right perfectly in the middle, but in the second time, the drone is up here hovering. So it's like within the 5 meter bound, but it's like somewhere up here. And then let's say in the next test, it's over here. Next test, it's down here. Next test, it's over here. Next test is over here. So it's going to that point, but it's always within a 5 meter radius of error. You just run the test over and over again, many, many times. And then, the average, if you run the test enough times using law of large numbers, and statistics, you can like average out the error, and obviously if you run an infinite number of times, you would settle on the actual centroid, of that point. And so, that's, you don't have to run it infinite times, but I think like you'd get a result, a very, very reliable result. And then again, having military grade GPS means that you just have to run the test. You probably don't even have to run the test more than once. That's the nice thing about it. But to me, it still can be done with a civilian grade GPS as a coordinate system. And then within that coordinate system, that I agree, in some ways assumes that the Earth is a ball, because it's a natural and elegant coordinate system to use if you're doing things over a ball. That's why people would use spherical coordinates. And then, but that doesn't mean you can't within that define, straight lines or a plane and all that. So if you imagine like taking a ball and you just like slice the ball from, any direction, it creates a plane. And, as long as the drone can operate reliably along that plane, you're good, and it doesn't have to, it's obviously not cutting the earth. I'm talking above, the surface of the earth, really in any direction and in any orientation, as long as it's straight, and so that is not difficult to have a GPS coordinate system and then put a slice through it and then understand what those coordinates are that are on that surface or very close to it, and then have the GPS only have an affinity towards that surface. And then once you can do that, which I don't think would be a major issue with these error bars taken into account, you have a ripe playing field for tests. And again, you don't have to fly the drone from one end to 50 miles down the road. You just have to be at one point, have it record it's the thing that's dangling from it with the water, preferably something welded to it, firm, and then show that, the thing is submerged in water. Have it reliably go to another point, even thousands of miles away, even in a completely different water body, and at a point that is, again, along this sliced plane along a sphere, and record what the drone's doing with the water beneath it at that point with these error tolerances. And again, I think something like that to me is very rigorous, because then again, you just do that whole thing over again. And the cool thing about this test is actually it could involve people from all around the world, because GPS is sort of a, available fairly ubiquitous. Like, again, coverage is very, very important. But, you just need a drone having the ability to go to places in using this GPS coordinate system, and then, do a test, as long as the drones are the same make and then the ball dangling from it is the same length. You don't even need to have the same person do the test. You can just have 50 different people in different parts of the world go to a specific agreed upon point in the GPS coordinate system, which it is, in spherical coordinates. And then, it would be done, and then the cool thing about this test is you just, let's say that test would be one slice, along one plane. And then, you can make another slice. You can do all different variations, which would then require having to engage people from different parts of the world, depending on, the points along those slice. what's beneath them, what physical land, what country is beneath them, what city. And yeah, I mean, I think something like that is fairly straightforward. So if anybody's interested in coming up with something like that, I think an engineering firm, in particular one who has access to resources around the world, that would be very, very simple for them. You don't necessarily have to do it that way, like I said, with different people in different parts of the world, because it adds a little bit of ambiguity, but you could still have a drone over one body of water, be flown out really far away, take the picture, do the test, and then have it come closer progressively, go to a new point, settle into that radius with the error, and then take a picture. And then, if the battery's running out, you just replace the battery and then have it go back to its usual planned course, its planned path, which again is predetermined by the GPS coordinate system. And so you might need to use two drones, like I said, daisy chain, but to create this straight line or flat plane dynamically. But I think there's a way to even do it with pre-planning, with just knowing what the coordinate system is, and then just calibrating it locally, like just putting a drone above the water surface that we're planning to do the test on, get the reading, and then move it a little bit, and then see what the reading is, and then just kind of in mathematics, just on paper, so to speak, come up with a pre-planned flight path. And then based on the geometry of the earth beneath it, two different things would happen with the interaction of that drone and the water beneath it. So to me, these kind of things are very much civilian, for us serfs, us people who don't have access to the very technology that we're paying for, that we're slaving away for. But this is the world that we live in. Very doable. And the error bars are very understandable. We can appreciate them because most people have a phone and can understand how accurate GPS is. Like if I took this phone and went up one floor, 2 floors here in my apartment building, I'm assuming I would get a different reading. I'll probably do that today, just to see what changes. But it's another good way. Actually, I remember earlier I was trying to get a feel for how high my high rise is, and I shot my laser for my they have laser rangefinders for golf within 500 yards. I could have actually just taken my phone to the first floor, read off what the GPS coordinate is, and then went to the rooftop, and then check what the elevation change was, and got a good estimate. So I could even calibrate my golf rangefinder estimate of the distance from top to bottom with the GPS on my phone. So there's ways to all I'm saying is there's ways to get a feel for GPS with things that are very much off the shelf, and we have available to us. And so something like this, I don't think is that far away. Hope everyone's doing well. Bye.